of x for which f dash zeta equal to 0 or 0 is less than this and this. Okay, this we have again verify. Here let me find out first f0 first condition. So let me prove this. Proof of this f0, the first condition. The first condition of Rolle's theorem. Let me verify first and then second. First condition of Rolle's theorem. That is fa equal to fb. That means at the end point the function value of the function is equal. Okay, so let me find out f0 is the first a. F0 is what? This is 0 minus 1, 1 minus 1, 0. This is 1 minus 1, which is 0. And what is f2? F2 is 1 minus 2 minus 2, 1. This is also 0. Okay, 2 minus 1 is 1. 1 whole 2 by 3 is 1. Okay, so this is also 0. This implies that f0 equal to f2. So first condition is satisfied. So first condition is satisfied. This function is continuous from 0 to this. First condition is satisfied. First condition is satisfied. Okay. Then the second condition. For second, we have to find out f dash x. F dash x differentiation of this function. So f dash x 1 is 0. This is minus sign 2 upon 3 power 4. This is x minus 1 again minus 1 upon 3 power, which is minus 2 upon 3 divided by x minus 1 power 1 upon 3 positive. Now here x equal to 1 again is not defined, it is infinity. If I substitute here x equal to 1, so 1 minus 1 is 0, something upon 0 is infinity, which is infinity for x equal to 1. Not defined, so not defined. We cannot define for infinity, so value is infinity. Not defined. Hence, f dash zeta, okay, equal to 0 is not defined, is not found, is not defined. We cannot find a zeta point in between this and this, for which this is 0. Here 0 is lying between this and zeta. There is no point, because x equal to 1, 1 is lying between 0 and 2. Here 0, okay. Here zeta equal to 1 and 0 is less than 1 is less than 2, but at 1, but at zeta x equal to zeta or equal to 1, the value of the function is not defined. F dash zeta is not defined, so the function is not differentiable at this point. It is not defined, hence Rolle's theorem does not apply here. Rolle's theorem does not apply here. Does not apply for this equation, for this function. For this function, okay. For this function, Rolle's theorem is not applied because we cannot find the point in between this and this. 1 was there, but 1 at 1, the value is not defined. Okay, the differentiability is not defined. The function is not differentiable in between and value of the interval, whatever is given. So this is not applicable. Now 11th question, the last one let me talk about. For the 11th question here, the question number 11 says, okay, it says discuss the applicability of Rolle's theorem to the function, this one. Here fx equal to x minus a whole power n, okay, into x minus b whole power n. It says in AB interval. So Rolle's theorem, to prove Rolle's theorem, let me find out conditions. First condition is fa is equal to fb. Let me find out whether this is applied or not. Here is applied or not. Let me check. Is applied or not? Let me check. Here A is equal to A is A, no problem. So let me find out what is FE. FA is equal to A minus A whole power m into x A minus B whole power m. This is 0 into something 0. A minus whole power m is 0. What is FB? Then FB is B minus A whole power m into B minus B, that means 0, equal to B minus A whole power m into 0 equal to 0. So this condition is satisfied. FA is equal to FB, verified. This is verified. Okay, first condition is satisfied for Rolle's theorem. What is second condition? Let me find out what is f dash x. If Rolle's theorem is to be verified, it's the proof of Rolle's theorem to the function this. Okay. So f dash x is equal to how much? Let me find out f dash x. This is x minus a whole power m as it is. This is n into x minus b whole power n minus 1 plus sign. Now x minus b as it is. This is m into x minus a whole power n minus 1. Now if I take x raised power x minus a whole power n minus 1 common and x minus b whole power n minus 1 common, so we will have, this is only x minus a, the first one, plus in this case, sorry, this is m into 1, sorry, this is n into x minus a. In this case, this is m into x minus b in this case. What I have done here, this is x minus b whole power n. Sorry. Okay, so this is x minus a whole power m as it is, x minus b whole power n as it is, and differential of x minus whole power n. Now from the first one, I have taken x minus a, the m minus 1 power common. Here we will have x minus a, but n is multiplied, plus m into x minus b. Okay. So here we have x minus a m minus 1 power x minus b whole power n minus 1. And the second point will be, in the second bracket we will have nx minus na plus mx minus mb. Okay, this is x minus a whole power n minus 1, x minus b whole power n minus 1. In the other bracket we have, let me take mx and plus nx. This is x common, m plus n. Okay, m plus n. From mx and nx we have taken x common, so m plus n, minus sign, nothing common. This is mb plus na. Okay, so let me find out what is the point. So zeta, if I find out zeta, f dash zeta, the first condition is satisfied. For second, if Rolle's theorem is applied, so that f dash zeta, let me take zeta point equal to 0. This implies that zeta, okay, this is equal to f dash zeta equal to 0, implies that x minus a equal to 0, or this x plus x into m plus n minus mb plus na equal to 0. This equal to 0, that means x equal to a. This equal to 0, all three are equal to 0 if I make. And x minus a equal to 0, that means x equal to a, which we already have. X equal to b, we have already have. But from this, there is another point. But that will be x equal to mb plus na divided by m plus n. Okay, so this point must lie. If I take it numerically, so whether the Rolle's theorem applied here, if this point lies between m and n, then Rolle's theorem is applied. Okay, for this the value will be 0. For this value, if I substitute x equal to this, the value is satisfied. Okay, even if I take numerical values, this value will lie in between this. If I take substitute, I mean numerical values in place of m, b and na, you will find that this point will lie in between a and b. Okay, so because m plus n may be larger value in denominator and this is greater than this, so that means this is greater than, this is smaller than b, but it's smaller than this. Okay, if this is there, if A is less than MB plus NA upon M plus N less than B, that means this point is lying between A and B. We substitute any values of this point will lie in between this. Then Rolle's theorem will apply. So zeta point, okay, this is the value of zeta, which is this MB plus NA in between A and B. So that then, okay, if this is lying between, then Rolle's theorem applied. Then the Rolle's theorem is applied. Rolle's theorem is applied. Okay, so Rolle's theorem is applied. So for the 11th question, Rolle's theorem is applied. For that, the value of x must be this, which must lie in between A and B. Okay, so at this point, the value will be 0. Hence, Rolle's theorem is applied. So this is the Rolle's theorem all about. Okay, next time I'll talk about the another theorem, which is again Lagrange's mean value theorem, okay, which is also very important. The same expansion of functions. Here we are talking about expansion of functions. In this, these theorems are given. Okay, so we are talking about these terms. Okay, now this is over. This lecture is over. In the next lecture, I'll talk about Lagrange's mean value theorem. See you please in the next lecture. And these are very important theorems which must verify with the help of numerical questions. I always tell my students that please pay attention towards the questions of these. Only then we can understand that what is Rolle's theorem. Otherwise, theoretically, if we just understand this, we are not going to apply this. Till we have applied in the questions form or verified that in the questions form, whether it's verified or not verified in these questions as I have proved, okay, that can clarify what is the Rolle's theorem basically mean. Okay, so that is all. Okay, then see you in the next session.